All right, let's look at our free body diagrams one-on-one. We'll start with the very basic force of gravity. This is the case of free fall. Remember, free fall is falling through space without any air resistance, when the only force acting on the object is force of gravity. So since there is no surface, no air, and the only thing that affects the object is force of gravity, that's all we show. If we are real, or realistic if you will, we can talk about force of air resistance that will be opposing force of gravity, and therefore our acceleration is no longer equal to g, which is the acceleration due to gravity, but it's a little less than that. At some point, as your velocity increases because you are accelerating, you're going to reach what is called a terminal velocity. Terminal velocity is when your force of air resistance equals force of gravity. So you're still falling down, but you are no longer accelerating. If you are referring to air resistance, finally, if you would like to stay alive, you will probably deploy a parachute, which will increase your force of air resistance. And in that case, your acceleration is now upward. Now, what if we have something on the surface? Well, I know that there is a surface. I know that there's force of gravity because it's an object, therefore it has mass, therefore it will experience force of gravity. Then, since it's on the surface, it's going to press on the surface, and the surface is going to return the favor and create a normal force. Remember, we call that force normal because it's perpendicular to the surface, not because it's not abnormal or crazy. Force of gravity, because it has mass. Force of normal, because it presses onto the surface, and the surface returns the favor with an equal force. Is the object moving? I have no idea. It could be. And if it is moving, it could be moving left, or it could be moving right on a frictionless surface. So, unless they tell me it's at rest, I cannot be sure. So if you see something like this, it could be sliding left or sliding right on the frictionless surface. So in this diagram, I see for sure that my object is moving to the right. So it's frictionless and the forces in the vertical direction are balanced. Now things change. Why do they change? Well, because I see force of friction directed to the left. Force of friction is that force that is opposing your motion. It wants to slow you down. So that gives me an idea that my object is actually sliding to the right. It's not being pulled, it's not being pushed. It's like a puck on ice, on real ice that is not frictionless. Something must have given it a push to the right, and now it's sliding to the right, and it's slowing down because my force of friction is unbalanced. And because force of friction is unbalanced, there will be an acceleration in that direction. So slowing down because it's moving to the right, but it's slowing down because force is unbalanced and it is directed to the left. Here, similar. See how here I know it's moving to the right because friction is to the left. Here force of friction is to the right, therefore my object is sliding to the left, again with acceleration. Something pushed it or pulled it, and then that force disappeared. So this is after a push or a pull that initially got our object in motion, and now force of friction is slowing it down. It might eventually stop altogether. Now, look at this. Here I have force of pull, definitely being pulled. Then I have force of friction, which is equal to it. And this little K right here, if I know it's K, that means it's kinetic. So since it's kinetic, that means that my object is in motion. And then since this force of friction, kinetic, and force of pull are equal, then I know that it's going to be moving to the right with a constant velocity. Newton's first law, if forces are balanced, an object in motion will remain in motion with a constant velocity. Here, notice how this right here is S. S for static. Therefore, our object is at rest. It is being pulled, but force of friction, static, is a very, very lazy force. If I pull with 5 and it has enough, it will give me 5 in return, and my object won't move. I pull with 10. If it has enough, it will give me 10. It will only exist if it has to work to stop you from moving. Does that make sense? Hopefully, yes. So the difference between here, it's kinetic friction, therefore I know it's moving to the right, and it's moving at a constant velocity because pull and kinetic friction are equal. Here, friction is static. I know it's not moving. It's being pulled, but it's not moving. Remember, force of static friction is a lazy force. It will not be greater than you pull. It will be just enough, and then your object will remain at rest. Newton's first law. So here, I know that my object is now, again, moving. And how's it moving? It's moving with acceleration because my force of pull is greater than my force of kinetic friction. So therefore, my object is definitely going to accelerate in this direction. It's no longer moving with a constant velocity because my forces are no longer balanced. Pull is outpowering kinetic friction. Boom. CP, children, don't panic. You don't really need to know much about this one because this is a pull at an angle. Honors NAP, drink it in. So force of pull here is at an angle, which creates a little bit of a component. Oops. So now gravity, which would have been balanced by normal force before, right here. Remember, normal force and gravity balance each other out here. However, in my case, in this diagram, I have a little bit of a pull upward due to the angle of the force of pull to the horizontal. And because of this, it's like if you put something on the scale and lift it a little bit, it's going to weigh less because scale is like normal force in this case. So therefore, because gravity is no longer supported by normal alone, it has a little bit of a vertical pull. So therefore, my normal and vertical pull will together be equal to gravity. So vertically, everything is balanced. Now let's look at horizontal. Horizontal direction, I have this amount of force of pull, which is like 3 boxes. And here I have force of friction, kinetic, also 3 boxes, which tells me that horizontally, just like vertically, my forces are balanced. Since this is kinetic friction, it's going to be moving to the right with a constant velocity. That is definitely static friction, therefore it's definitely not moving. And again, force of static friction is not greater than force of pull on X. It will not be greater. It is just enough to balance this out, and therefore my object is at rest. So this angle right here creates a negative or downward component of force of pull. So normal force is no longer less, but normal force has to support force of gravity that is pushing into the surface, plus my force of push creating a vertical part. So this vertical part plus this gravity will be balanced by normal force. So normal force in this case, I will say force normal equals force of gravity plus Fp. If this is my theta, it's going to be times sine of theta. They have to add up in order for our object to be balanced vertically. Now, in terms of horizontal, I know that this right here is my static friction, and it equals exactly force of pull X, the X component, the horizontal component of my force of push or pull. So when we have an incline, force of gravity is still straight down. However, because of the incline, now we have 2 components of force of gravity. We have the vertical component, even though it's sideways, it's vertical. And this is horizontal. It is along the incline. So this is our surface. This will be my normal force. This will be my force of friction along the surface, right? Technically, strictly speaking, this is my surface. But remember, we show all our forces at the center of, in the imaginary center of gravity for our object, just to make it easy, just 1 dot. So we have force of gravity, Y component is supported by normal force, and then force of gravity X, if I see visually that my force of friction is equal to this mgx, or force of gravity X, then I know that my object can be either at rest, so it's not sliding down the incline, it's just sitting there, or it might be sliding down if this is kinetic, and I don't know, they didn't tell me static or kinetic, so it could be both. My object could be sliding down with a constant velocity. Now if I look over here, then this definitely is longer than force of friction. So it's definitely sliding down. Not only is it sliding down, it's sliding down with acceleration because my mgx is greater than force of friction up the incline. So it is outpowering it and it's therefore accelerating. Now, if we do have something pulling it upward, now I will be comparing my force of pull. I don't know what kind of force of friction this is. It could be force of friction static, it could be force of friction kinetic. If it is force of friction kinetic, then my force of pull being equal to friction and mgx would create a constant velocity up the incline. If this friction is static, then I know that I'm pulling, but force of friction is giving me just enough to compensate for the difference between my pull and Fgx. So therefore, this could be at rest or it could be sliding at a constant velocity. And here, force of pull is definitely greater than my force of friction plus mgx. So my object is going to be speeding up the incline. If you understand the basics, you should be able to figure out more complicated examples. If you need more practice, I would recommend drawing those. Give yourself a scenario. Is it moving up incline, down incline? Is it accelerating? Does it move with a constant velocity? Up incline, down incline? Is the pull at an angle? Is it a push into the ground? So give yourself various examples. All right, I hope this helps. I will see you in class.